Welcome back everyone. In this lecture we will continue with the representation theory of finite abelian groups. As we noticed earlier, so we can actually classify all the irreducible characters of finite abelian groups very easily in terms of actually the group itself. So, let me just recall what we were actually doing in the last class. So, we fix G to be finite abelian group. So, then we immediately have that the irreducible representations of G, they are one dimensional. So, all irreducible finite dimensional representations of G, they are one dimensional. So, in particularly we can identify actually the representations, irreducible representations with its irreducible characters. So, we do not need to actually distinguish them because we are working with one by one matrices. So, in particularly we take this home G C cross, this is the set of all group homomorphism from G to C cross. So, this is the set of all group homomorphism from G to C cross. So, this is the set of one dimensional irreducible representations of G, and this can be identified with the set of irreducible characters of G. So, this is same as the set of irreducible characters of G, which is same as the set of irreducible representations of G. Okay, so, because of this we are going to only work with this particular set. Since G is assumed to be finite, we can actually make further restriction on this set. Indeed, if we think about it, since G is finite, all the images of given homomorphism, they are going to lie in only the unit circle because they are all roots of unity. So, this is same as the home G S 1. So, home G C cross is same as home G S 1. Okay. So, this is what we are going to call it as G hat. So, which is the dual group of G. So, this is the dual group of G. So, ultimately what we want to prove, the dual group is indeed isomorphic to G itself whenever G is abelian group. So, what is the actually group multiplication here in G hat? The group multiplication is given by actually pointwise multiplication. So, let us take chi 1 and chi 2 from G hat and then define the following pointwise multiplication chi 1 chi 2 of G. So, this is going to be equal to chi 1 of G times chi 2 of G, and this is how it is defined for all G in G. And this multiplication, so this is what we call it as pointwise multiplication. So, with this multiplication, so this G hat it forms a group. So, G hat with this pointwise multiplication is a group. Indeed, it is abelian group. And we are going to show that later G hat is indeed isomorphic to G itself. Okay, so, why this is indeed a group? So, I am going to leave it to you to check the pointwise multiplication is indeed again element of G hat. So, I will leave it as exercise that given chi 1 chi 2 in G hat, we have chi 1 times chi 2, that is again in G hat. So, indeed we need to check that chi 1 chi 2 is again group homomorphism. So, that is easy to check. And what is the identity element? The identity element is defined to be chi 1. So, which takes value 1 for all G in G. So, this is a trivial group homomorphism from G to C cross. So, that is going to be the identity element of this dual group G hat. So, this is the identity element. Now, what will be the inverse of given chi? So, given chi in G hat, it is not difficult to see the chi inverse is defined to be you take chi G bar. So, this is how you define the inverse for all G in G. So, in particularly we have the closure property here and the identity element as well as this inverse. Associativity will come for free because these are all complex valued functions. So, this will tell us that G hat is indeed a group, and since all values are actually complex value. So, in particularly it is not very difficult to check chi 1 chi 2 is same as chi 2 chi 1. So, this is indeed abelian group. Okay, so, why this is indeed isomorphic to G? So, that can be checked by reducing it to the finite cyclic groups using the structure theorem. So, let us first do it for the finite cyclic groups, then we can actually generalize to any given finite abelian group. So, again I am going to leave it as exercise. These are all not very strong statements to prove. So, if you start with G, which is just a cyclic group of order m. So, then what we can do, we can identify the G hat with the following characters. So, the elements of G hat, they are all called irreducible characters or just characters of G. So, they are nothing but listed as chi naught, chi 1 etcetera, chi m minus 1. So, where chi I we already defined this some time back, but anyway let me repeat. So, chi k, which is defined on the class L, is exactly equal to given by e power 2 pi I k L divided by m. So, for each k from 0 to m minus 1, so we define the function chi k. So, which is a map from G to C cross. So, what we do, we just pick basically the mth root of unity, which is 2 pi I divided by m, sorry 2 pi I k divided by m. So, this is the mth root of unity that we are choosing for each k. So, then you just define this chi k evaluated on this class L to be this function, and it is not difficult to see this is indeed a group homomorphism from G to C cross. So, in particularly we have m number of elements in G hat, and it is actually indeed a very easy thing to prove that the following map that actually defined by the class K mapping to chi k gives actually isomorphism between G and G hat. So, I am just going to leave it to you to check. This is indeed giving you isomorphism between G and G hat. So, here what we need to prove? So, we need to prove this is indeed group homomorphism and as well as this is onto. Okay. So, this is the exercise basically. Okay. So, now how to deal with the general finite abelian group. So, for that we want to use the structure theorem. So, what the structure theorem actually says, so the structure theorem asserts that given any finite abelian group can be written as product of cyclic groups. So, in particularly we can write G as the following product of cyclic groups. So, you can write it as direct sum of this G modulo N1 G etc. G modulo, let us call it M1 etc. MRG. So, you can choose these MIs such that this M1 divides M2 and so on, MR minus 1 divides MR. So, this is actually follows from the structure theorem. So, now once we know that G can be written as direct product of cyclic groups. So, now we need to understand what happens to the dual of the product. So, indeed it is not difficult to prove that if we take A and B to be two finite abelian groups. So, then if we consider the dual of the product, so that is going to be naturally isomorphic to the product of the duals. So, A hat cross B hat. So, this just follows from the fact that if you start with the group homomorphism from A cross B to C cross. So, if I take group homomorphism from A cross B to C cross. So, then we can actually restrict this homomorphism to the two copies, one copy of A. So, that is A cross 0. So, where 0 I am calling that is identity element of B. So, this let us call it as chi A. So, what is chi A? So, chi A is just nothing but chi restricted to A cross 0. And similarly, we define this chi B, which is chi restricted to the copy of B inside A cross B. So, chi B is nothing but chi restricted to the copy of B inside A cross B. So, now it is not very difficult to prove chi is uniquely determined by chi A and chi B. So, chi goes to this map chi A and chi B. So, this defines an isomorphism from the dual of the product to product of the duals. So, now if we put back together this structure theorem, you can see that. So, the dual of G hat is going to be product of the dual, but we already know that individually these are actually isomorphic to Z modulo M1 Z, and this is isomorphic to Z modulo MR Z. So, in particularly this is going to be isomorphic to Z modulo M1 Z cross etc. cross Z modulo MR Z, which is exactly isomorphic to G. So, indeed from these isomorphism you can see that the isomorphism between G and G hat, that is not going to be natural. This is because, so here actually when we actually took the generator, cyclic generator of Z modulo M Z. So, we have made actually the choice 2 pi I divided by M, but we could have chosen any other cyclic generator, and then that cyclic generator is going to determine this isomorphism between Z mod M Z and then its dual. So, because of that you can see that the isomorphism that we have actually between G and G hat, that is not going to be unique or natural. So, that will depend upon the generators that we choose for each individual cyclic subgroups. So, but this indeed actually proves that G dual is going to be exactly isomorphic to G. Okay, so, what is about the double dual? So, the double dual again from the same reason it is going to be isomorphic to G, but we have a very natural map that actually connects G with G double dual. So, here is the theorem. So, again take G to be a finite abelian group. So, then we have this natural evolution map. So, we define this evolution map from G to G double hat. So, what this map does, this actually takes an element of G and then sends it to the evaluation G. So, where this evaluation G is just evaluation at the element G. So, it is a map from G hat to C cross, where what we do, we take some character chi and then we evaluate at G. So, you just take chi of G as the value of evaluation of G at chi. So, this is indeed a natural map from G to G double hat, which actually associates G with its evaluation. So, this is what we are calling it as evaluation at G. And one can prove that this is indeed an isomorphism. So, this EV is an isomorphism. So, this kind of duality actually holds in general for the characters of locally compact abelian groups. Maybe later when you are interested in studying more about infinite groups, so you can actually look out for some similar statements for locally compact abelian groups. In a way, like this is all kind of leads to Fourier analysis, but right now I am not going to get into that, but later maybe if we have time. So, I will actually focus on actually Fourier analysis on finite groups. So, that will be done in the future. Okay. So, with all this we can see that already what we wanted to prove. So, maybe let me just write it very explicitly. So, if we take two abelian groups, so using the structure theorem, we already observed that in order to understand irreducible representations of given abelian group. So, we can decompose that abelian group into direct product of cyclic groups, then we can focus on individual cyclic groups. So, that is because the pointwise product that actually will take care of getting irreducible representations of the bigger group. So, let me state it as proper proportion. So, it is enough to consider only direct product of two abelian groups. So, let us take G 1 and G 2 be finite abelian groups, and suppose that cardinality of G 1 equal to m and cardinality of G 2 equal to n. So, then we can actually assume chi 1 etcetera chi m and phi 1 etcetera phi n, they are the irreducible representations of G 1 G 2 respectively. So, these are all the of course finite dimensional irreducible representations of G 1 and as well as G 2 respectively. So, now we are interested in creating irreducible representations of the product G 1 and G 2. So, it is all hidden in this isomorphism that we have actually established here, but I am just writing it very explicitly here. So, now we are interested in constructing these irreducible representations of G 1 and G 2. So, we already know that there should be exactly m times n number of irreducible representation of G 1 cross G 2. So, we will directly actually define them. So, the following functions, then the functions alpha I j, which are defined to be functions from G 1 cross G 2 to C cross. So, we define it for all I between 1 to m and all j between 1 to n. So, they are defined as follows. So, alpha I j of G 1 and G 2. So, that is exactly given by chi I of G1 and then phi j of G2. So, basically given two representation chi I and phi j. So, we will be able to produce one dimensional representation of G1 cross G2. So, we have not introduced the terminology tensor product. So, if we actually think about in terms of the tensor product, this alpha I j is nothing but the tensor product of this chi I and phi j. So, but here it is not very difficult to see what is the representation. So, we can directly write down what should be the representation as homomorphism from the group to C cross. Okay, so, in order to prove these are all given irreducible representations of G1 cross G2. So, we need to prove two things. One is that alpha ij's they are all group homomorphisms. So, in particularly they define one dimensional irreducible representations of G1 cross G2, and whenever alpha ij equal to alpha kl, then we should get that ij pair is same as k pair kl. So, then from this we can actually get m times n number of irreducible representation of G1 cross G2, but from our earlier observations there should be exactly m times n number of irreducible representation of G1 cross G2. So, from that we conclude that this alpha ij they form a complete list of irreducible representations of G1 cross G2. So, the claim is this alpha ij form a complete list of irreducible representation of G1 cross G2. Okay, so, why they are actually group homomorphism? Again, that is very simple exercise. Maybe let me just do it. If I take alpha ij and then take product of these two elements G1 G2 times G1 dash G2 dash. So, then this is going to be exactly equal to alpha ij G1 G1 dash and then G2 G2 dash, which is by definition is going to be exactly equal to chi I applied on G1 G1 dash and then phi j applied on G2 G2 dash. So, now using the fact that chi I phi j they are group homomorphisms, we can collect this as chi I G1 times phi j G2 and times chi I G1 dash and then phi j G2 dash. So, I have used the group homomorphism and everything happening in C cross. So, they are all commutative. But now note that, so this term by definition is nothing but alpha ij G1 comma G2, and similarly this term is nothing but alpha ij G1 dash comma G2 dash. So, that means alpha ij is a group homomorphism. So, in order to prove they are actually distinct, suppose assume that alpha ij is same as alpha kl. So, now what we can do, we can just restrict to one component and then see that chi I of g, so which is exactly same as alpha ij g comma 0 for g in G1. So, then this is exactly equal to alpha kl g comma 0. So, which is exactly equal to chi k of g. So, this actually true for all g in G1, that implies that chi I equal to chi k, but they are all distinct unless I equal to k. So, this proves I should be equal to k. Similarly, one can actually prove that j must be equal to L. So, that would imply that the pair I comma j is same as the pair k comma L. So, in particularly alpha ij's are all distinct. So, they are we got exactly m times n number of irreducible representations of G1 cross G2. So, that proves that this entire set alpha ij form a complete list of irreducible representations of G1 cross G2. Okay. So, now from this like I said, one can use the structure theorem in order to actually get irreducible representations of any finite abelian group. You write G as product of cyclic groups like Z modulo M1 G cross etc. cross Z modulo M or G. So, you can choose Mi such that this M1 divides M2 and so on divides Mr. So, then if you are interested in irreducible characters of G or irreducible representations of G. So, what we need to do is just take a product of irreducible representations of the individual ones. So, we can actually list, for example, like chi1 1 etc. chi m1 1. So, let us say this is irreducible representations of G modulo M1 Z, and then chi 1 sorry 2 1 1 2 etc. chi M2 2. These are irreducible representations of Z modulo M2 Z and so on. So, if we fix these notations, then it is clear that what should be the irreducible representations of G. So, we can define this alpha I1 etc. IR. So, which is going to be on this G1 etc. GR. So, it is given by you take chi 1 I1 G1 times etc. chi or IR GR. So, the powers indicate the which group we are talking about, the second group or first group, and these indices actually represents what representation that we are taking in that particular group. So, in particularly you can see that so when you take in the first group I1 character and then in rth group IR character. So, the product of them is going to give you complete list. So, these alpha I1 etc. alpha IR, where I1 varies from 1 to M1 and then IR varies from 1 to MR. So, this will form a complete list of non-isomorphic irreducible representations, non-isomorphic irreducible representations of G. So, this is how one will be able to get all possible irreducible representations of G for given finite abelian group. So, maybe you can take it as exercise and then do it for like G modulo 2 Z power R and so on. Okay. Take it as exercise, and then maybe you can find out some more explicit indexing set, and then you can have like very explicit list of irreducible representations of this particular group. Okay, so I'll stop here. So we will continue with proving that the degree of given irreducible representation divides the order of the group for any given finite group G.